Welcome back once again, ladies and gentlemen. We are working through chapter 18, where we are talking about sampling distributions. And in the previous video, or videos in this series, we talked about sampling distributions for proportions, and then we did some examples of those. And then in the last video, we talked about sampling distributions for means, and how they are slightly different as to which normal model we are using when we're looking at them. In this video, we're just going to do some examples of some application problems that we might use for sampling distributions of the means. So coming up first, we're talking about SAT scores. So SAT scores have a mean of 500 and a standard deviation of 100 and are fairly normally distributed. Create a sampling distribution using the 68, 95, 99.7 rule for a random sample of 20 students. So before we do anything with our rule, we need to make sure that it is okay to make a sampling distribution with the data we have here. So we need to check the conditions. And again, whenever you're doing any problem using a different model, you need to check the conditions to make sure the model works. And in AP land, where you're taking the AP test, there are points assigned to you writing out these conditions. So it's something that we need to remember and mark on all of your questions, because it is something that is graded on the AP exam. So the conditions we need to check were, is this a random sample? So we need to write something to the effect that says that this was a random sample. It did tell us in the question prompt that it was random. So we might say something like the question states that SAT scores were polled, randomly. Therefore, this condition is met. And again, we want to have this format where we say we state evidence that it has been met, and then we need to state that this has been met, right? Give our evidence and state that it was met. We can't just like put a check mark, right? I've had some students do that. We would just check it's good, right? No, that's not enough. You need to give evidence as to why it is good and then state that it is good. So in this case, the question states that the SAT scores were polled randomly, therefore this condition is met. Next, we need to talk about, is this large enough? Is our sample size large enough? And you know what? 20 students is actually pretty small. However, the sample size, even though it's small, it does say it's normally distributed. And so as we said in the last video, a smaller sample size is okay if we believe that the population is normally distributed. So what we might write for this one is that the sample size is small. However, because the population is normally distributed, this condition is met. Right? So these two conditions have been met. We want to write something to the effect that says conditions have been met for a sampling distribution. So we've decided here that because the conditions have been met for it, we can use this sampling distribution. So let's go ahead and do it. We can use the normal model. The normal model we're using, remember, this is quantitative data. So the mean is going to be close to the population mean, which is 500. But the standard deviation for the sampling distribution, is follows the formula, the standard deviation divided by the square root of n. So in this case, we have 100 divided by the square root of 20, which, doing my calculations over here, gives us, oops, I did something wrong. Oh, there's a random thing there. Okay, 22.36. So there's my normal model that I'm going to be using for this. Again, the notation here is it's a normal model with a mean of 500 and a standard deviation of 22.36. Now we can make our distribution using the 68, 95, 99.7 rule. So I'm going to draw my normal model. And I'm going to be short on space a little bit here. But the mean was 500. So that goes in the middle. And then we're going to go up 22.36. So this is 522.36. And then we're going to add that to add one more standard deviation here. And that gives us 544.72. Those look like 9s, but they're actually 2s. And then we're going to add it one more time. And we're going to get 567.08. Now we need to go in the other direction. 500 minus 22.36. And that's going to give us 477.64. And then down again gives us 455.28. It's getting really small down there. I should have planned this better. And I say I should have planned this better as though I couldn't just, like, you know, stop the video and just do it the right way. But why would I do something like that? The last one is 432.92. So we can say that 68% of the data falls between 477.64 and 522.36. Meaning that if I were to take random samples of 20 students, 68% of those samples would have a mean score between 477 and 522. And if I were to take the many samples of 20 students, then 95% of them would fall between 455.28 and 544.72. And then again, 99.7 of those samples of 20 students would fall between 432.92, ew, ugly, and 567.08. And there we go, right? So we've used our sampling distribution. Again, the standard deviation changes to create that normal model with the 68, 95, 99.7 rule. Let's move on and look at our next example. So the speed of cars on the highway have a mean of 52 miles per hour and a standard deviation of 6 miles per hour, and are likely to be skewed to the right, as though because there's a few fast drivers. Describe the distribution of the mean speeds in a random sample of 50 cars. So again, we need to check conditions first. And so we need to say, is this random, and is this is this large enough? So checking conditions here. Randomization. It does state that there was a random sample of 50 cards. So we say the question states that cars were pulled randomly. Therefore, this condition is met. The other condition is this large enough? And the sample size here is 50. And so we can say 50 is a large enough sample. Therefore, this condition is met. And then we say conditions, because both of them are done, we say conditions have been met to create a sampling distribution. So the conditions are good. It is okay to use a sampling distribution for this particular set of data. Let's go ahead and calculate what that one's going to be. I'm going to erase the screen, so be careful if you're copying some things down. You should pause the video. You should have paused it a while ago. You're gonna have to back up the video and pause it now. Anyway, the normal model that we're gonna use has a mean of 52 because the mean on a sampling distribution is similar to the population. The standard deviation, however, is different because it is a sampling distribution. It does get a little bit smaller to the fact that it's the standard deviation over the square root of the sample size. So for this case, it's going to be 6 over the square root of 50. And looking at my calculator here, 6 over the square root of 50 is 0.849. All right. So the normal model that we're going to use is a mean of 52 and a standard deviation of 0.859. So let's go ahead and draw out our normal model and use this 68, 95, 99.7 rule. So here's my mean at 52, and then I'm going to add that standard deviation 3 times to see the values that that's going to be. And so I get 52, let's see, the first one here is 52.849. And then the second standard deviation is going to be plus 8.849, which will be 53.698. Ooh, that's getting ugly. 53.698. And then the last one here is going to be 54.547. We need to go in the opposite direction now. So we do 52 minus 0.849 and get 51.151. And we get 50.302. Uh-oh, school's over. I better go home. And then the last one here is 49.453. So there is my sampling distribution for the samples of size 50. We can say that 68% is between 51.151 and 52.849. 95% is between 50.302 and 53.698. And 99.7% is between 49.453 and 54.547. Let's do one more example. This time we're going to talk about birth and babies. So at birth, babies average 7.8 pounds with a standard deviation of 2.1. A random sample of 34 babies born to mothers living near a large factory that may be polluting the air and water shows a mean birth weight of only 7.2 pounds. Is that unusually low? So a question like this comes up because we're wondering, is this factory's pollution causing birth weights to be low, which can cause health issues? So things like this come up, and so this I put this I like this example because it kind of shows sort of the important weight sometimes that these questions can answer. We need to check conditions. We're getting pretty long on the video here, so we need to check them. We need to write them all out. However, I am just going to say this time that randomness does work because I'm not going to write it out. That the random sample, it says in the question that it's a random sample. Therefore, this condition has been met. You need to write it out, though. I'm just trying to save time. And then, is this large enough? 34 is getting to be about medium range. So it's probably large enough. We would also expect that birth weights to be fairly normal. So this one is definitely checked as well. Okay. Again, I'm saving time by not writing this. You should never ever do this. Do as I say, not as I do. I'm trying to save time for you here. So let's look, how do we answer, is that unusually low? Well, we want to look at the sampling distribution, right? What does a sampling distribution of 34 babies look like? Well, the mean is going to be 7.2, but the standard deviation is going to be the standard deviation over the square root of n, which is 34 divided by the square root of, I did that wrong. It's 2.1, we got this, right? Divided by the square root of 34. I'm going to write this over here. 21 divided by the square root of 34. Not 21, 2.1. Gosh. Maybe I should just end the video now because I apparently should go home, right? The bell rang, and my brain decided to check out the moment that happened. Let's try this again. Okay, so this is 0.36. So the model itself here, we can draw the normal model, and that's not a good one, but oh well. This just gets worse and worse. The mean here is 7.2. It's asking if this is unusually low, so I'm actually just going to draw out the left side of this model. So 7.2 minus 0.36 is giving us 6.84, and then we're going to subtract nope, it's 7.8. Oh gosh, this is just, I should just redo this, but I'm not gonna because I gotta get this done. We're gonna try it again. 7.8 minus 0.36 is giving us 7.44, and then we're gonna subtract 0.36 from that, and that's going to give us a 7.08. And I'm actually going to stop it right there because we can see that 7.2 is going to fall somewhere in between here. So it's about 1 point something standard deviations away. If we really wanted to calculate that, we could figure it out with our z-score. And say 7.2 minus 7.8 over 2.1. Nope, I'm wrong, 0.36. And we can calculate what this exact z-score would be, which is negative 1.67. So is that unusually low? No, it's not, right? 2 standard deviations is unusually low, but 1 negative 1.67, it's approaching it, but it's probably not that unusual. It's certainly lower, but it's not so unusually low that we don't think that it could have happened by random chance. So that's it. That's what we've got for today. This is the last of this Chapter 18 videos. If you've got questions, comments, concerns, please make sure you address them here, and I will do my best to help you. But thank you very much for watching, and I hope you guys have a fantastic day. Bye.